See, slow motion like that is, it's like a super expensive camera because that guy, he's bouncing about 80 times.
Yeah, he does it on cheap. They spend some more money on getting photography and a few other things.
The other funny thing is the different sizes of droplets. One's like way hard to see.
Yeah.
Like
Of course
that.
it is.
They're too big to see. I still don't understand like what's physically actually happening, but I'm assuming it's just a certain
They're all
thickness
bottled.
now. It's not
Cushion of air,
No.
now the droplet doesn't merge with the
Yeah.
liquid. It's well, it's a combination of a cushion of air that blocks it, so it's compressing the air,
There's two different kinds of atoms.
and that's enough to keep them apart.
They're the same strength, so.
That's why it's very delicate. You have to have all the right frequency and viscosity.
I knew it had something to do with air. So it's like almost like you say cushion air, it's almost like the air pressure somehow it's what's causing the force that's counteracting gravity.
Air has to move out of the way for the droplet to come in contact. So it's pushing on the air, and the air can't move fast enough to get out of the way. So it causes an air bounce. Do an air bounce with the frisbee. You know how to do that?
You bounce.
Throw it down on the ground and it'll bounce off without hitting the ground. It might actually hit the ground. I don't know. I think I've seen some people do it without it touching.
Wow, that's pretty amazing.
Yeah. But anyway, the idea is it's the air doesn't have time to get out of the way, and it forms a cushion.
But calculating the physics for it, like he actually like apparently Dr. Beal, he told me he finished the equations for it. The equations for motion apparently and all that. And I'm curious, like, is that that's like a lot of hydrodynamics, right? That's not what you get in undergrad. Apparently you don't get that.
I know what it means.
Yeah, these guys that made these videos are in the applied math department, and like they overlap a lot in the fluid dynamics. So I didn't know a lot of fluid dynamics.
So did I have any hope? Do I have any hope after my undergrad career? Actually making
I didn't end up doing 5 or 6.
Yeah, you could.
I didn't have time.
Do it.
And maybe I could figure it
Fine.
out. But see, I ended up with both. I ended up with this, and I didn't see anything like it was complete. So it's
Dr. Beal was talking about how you need to use
like 6.
you maybe first study calculus variations. Then from there, I learned tensor analysis. Apparently, you use that to like. But hydrodynamic.
I thought it was like 13.
It is, but the hydro is, because it's isotropic, there's a lot of, I'm not sure. You have a question?
Yes.
You want to work everyone. Well, so you have a transform of. So in that case, then you're right. 11:15.
Oh.
Sure.
So I get 5 weeks off for this whole semester.
I guess so.
It's not bad for me.
Yeah. There's no issues, yeah.
No, you want this to correspond to last.
Yeah.
Yeah, but
Yeah.
that's another problem.
Your problem is different.
No. No, is it yardage or yard?
Yards.
Okay, good, all right. Okay, so, Mary was like, I knew it was some different values.
Yeah, I did that.
You do like running in high school?
Yeah.
You seem like a guy in soccer, you seem like a guy who did hurdles.
Yeah, this is just the.
What?
Used as a placeholder.
You have, looks like you have really long legs.
So in the table, expert like this was the placeholder. And you look in for particular problem, you transform it to a function.
There's a
The
20.
lambda squared is equal to 4 sigma naught squared.
I did on my notes.
Then you can use what's in the table and just substitute.
I'm missing
2
one
sigma
page
naught
now,
for
so
everywhere
it's
there's
from
one.
Friday before
I think I
we
see.
left the fall.
Oh, crap. Okay.
I just haven't watched it yet. That was
Yeah.
what, 9?
That's just a-
12, 11.
Right here it is. So it's just a placeholder. So you look for something that's the right functional.
Oh, I don't know where she is. She has an exam.
And then there's gonna be a particular value of lambda that will make it match exactly what you
Man, I hope people show
I
up.
thought it was like an actual
It's a
symbol.
Wednesday. I normally just skip on Fridays.
Well, that's what a symbol is.
Well, it's
right?
like
It
an
points
act-
to something, whatever you want it to point to.
There you
I
go.
felt like whatever you had you have the land
I don't know, my friend made it, and she's like, it's
Yeah,
life changing,
so
and now I don't got my phone anymore.
There's a kind
I'm
of
scanning
validity.
photos.
It means,
Good way to
but
pass
you don't
the
have
time.
any intrinsic.
Yeah.
That's like doing that.
That's what you have to find a best.
Yeah.
Can you
That's
defer
why
to
you-
real quick?
And which makes it powerful because it
Probably
can be anything you want it to be. Right, so you have an entry
Is it full?
table like this.
Oh, maybe it won't.
Lambda
What's
doesn't
it?
have a particular
Didn't
value.
know that.
It's
Oh,
only generic.
The problem is when,
Yeah.
yeah, it's transforms, that's the problem.
Like that, wherever lambda.
Obviously, if it's like rotating or something.
Yeah, I also know how it's pointing to
It's
like
like,
Yeah.
this way, a lot
maybe
more.
my lambda has.
Ruins it.
Yeah.
Soil it, it's soiled it.
Did you just look at it somewhere yet?
Yeah, it's here.
They're not there.
I haven't looked at it. I don't look at it until like 2 hours before it's due, and it's a problem every time.
Normally it's insanely easier, right?
No, I cheat on all the homework, so I really couldn't tell you. I Google all of it all the time.
Teacher.
I don't know shit. I don't know what's going on in that class at all, ever. I get the notes. I get when he's speaking. After that,
You just like use something.
It's funny how you just connect energy to connect energy.
it's a lot of, he drops a lot of syllables in the words. And it's not the biggest problem for me, but parents do the same
You know,
thing.
something that matches.
But every once in a while, I can't figure out.
What you're saying.
So I look at the notes on my laptop, and then I'm like, oh, apparently someone I can't read this writing. I don't.
Yeah, his R is all like gamma.
Yeah.
And it's like, oh my gosh, like, and he uses gamma. So it doesn't help. I think it's together.
There's another one that really throws me off
It's
very
not like
well.
using X to represent.
I forgot what it was. It was
It
from the notes literally from yesterday.
It's not fun to kill something.
Could be me, I'm very easy to kill.
Yeah. Give you some brown bread.
Yeah,
See, I got
no,
one
it's
and
not.
two tough.
Literally
And I
almost
got down
anything.
here is where I started getting.
Right.
I literally put- I don't.
Okay, please take your seats.
Oh, no, it's okay. I'm doing it.
I gotta print this out.
Unfortunately, Dr. Villa not able to get this demonstration working, but the timing is such for the demonstration. I wanted to show you what you were going to see, or at least indicate to you what you're going to look at. Okay. All right, so this is an experiment that was devised. I think it was originally discovered by accident by some undergraduates at the University of Paris. And since then, it has provoked a lot of interest. It is not a quantum mechanical system in the sense that it does not display behavior like an electron in an atom, but there are a lot of resemblances between this classical system and the particle and guiding we're looking at here. So that's why I'm showing it to you, to try to provoke your imagination. So the intellect can use the imagination. The imagination is tied to the senses. When you imagine something, you're imagining something particular. You can imagine things that don't correspond exactly to what you've seen before. You can imagine that this room is painted pink.
Like your
You've seen walls and you've seen pink. So you can make combinations like that that don't actually exist in reality. Imagine a pink elephant or something. So you can get carried away with using imagination, but if carefully guided, the imagination can be used by the intellect to help you think about things. And that's what this is suggesting. So this is not, remember, this is not, don't make it too specific, don't make it too concrete. The idea here is that we have something that's kind of like a particle and something that's like a wave. And the particle is generating the wave and interacting with the wave that it generates. Okay, so we have an instrument here that's just, well, you saw the thing here, it was just a speaker with a pure mode generator, sound generator. And then a little dish, plastic dish about that thick, about that deep, with a particular liquid, very carefully chosen for the right viscosity. It's a silicon based. And then shake at audible frequencies. I guess it's kind of lower than audible, right?
Yeah, 40 to
Low bass.
80 times a second.
What is it?
Around 40, there's a Goldilocks range, so 40 to 80 times a second. Anywhere between there.
40 to 80 hertz. That's pretty low. Right, mid range on the piano is 400, 500 hertz. So it's pretty low. But audible if you turn it up high enough. And so it's shaking. And there's an instability at that right frequency. There's an instability. How do you generate the droplets?
So what we do is we take a syringe, a needle, and we put it into the bath while it's shaking, and we flick it up, and it causes a drop from the tip to come up and bounce on top of the surface.
So I've seen people use a toothpick for this, just kind of like at the top of the surface, and it creates a drop. Now, ordinarily, the droplet's going to just go up and then and come back down and melt back into the liquid. But with the shaking, something else happens. You have to have everything, you have to have the parameters at just the right range, which is why probably this was all discovered by accident, because you might not even try to do this. It's pretty surprising. Watch what happens here. So this is pretty nice photography. The droplet's been made, and you can see the reflection in the liquid below. And you can see you'll see the surface moving up and down. And so this is slowed down really a lot. And the droplet's really small, size of a toothpick, end of a toothpick. Look at that. Isn't that cool? Why is it doing that? Okay, so you can see the surface is shaking twice, 2 periods by the time the droplet goes up and back down. And then it interacts with the wave that it made the last bounce. And there is a cushion of air that this droplet is coming down fast enough that the air can't get out of the way. And so there's a cushion of air between the two that keep them separated. So otherwise the droplet, it could make contact would just get absorbed into the liquid. But it's stable. So there's enough surface tension on the droplet along with the air cushion that the thing will keep going like this. Do it for hours, right? Just get it going. So Dr. Padilla had Mr. Rudland working in his lab, so they made one of these yesterday.
Why does it almost stop?
Yeah, isn't that cool? I know. So some of it is like, okay, I gotta explain what that is. Yeah, so there, the droplet is influenced by the air cushion as well, so it's not just coming back down. So you're seeing the effects.
So the air's kind of pushing up a little bit.
So let's watch this again. So this was made by a lab at MIT. They took over this was initially published by people at the University of Paris, caused by stir, just cool for one. But also it resembles this idea of a guiding wave with a particle. The particle is generating the wave, and then the particle interacts. Okay, now this is kind of misleading photography, but in order to speed things up a little bit, because this gets that was not very long, right, in time. So to speed things up, they strobe it. So instead of, you've got a camera that's hooked up, that's taking a frame at a certain point in the cycle. So you're not getting the full jump, but you're getting where the droplet is at each point, at the same point in the stroke in the cycle. So you can see it, instead of watching all the bouncing, you see the translation. It's walking on the surface. And you can get this thing to walk on the surface, and again, you have to get the conditions exactly right. There are various other conditions where the droplet will just stay in place, and others where it's walk around. I got all kinds of stuff on the chat here already.
And how is it like just staying at the exact same height?
Yeah, because that's the strobe effect.
Oh.
The thing is coming up and down like this, and you only flash the camera when it's at the same point of the cycle, and so it looks like it's just staying at the same height.
So between bounces, it probably does alternate height.
Oh yeah, it's doing all that you saw before. But we're just taking a picture when it gets to the same height. And so all of that jumping has been taken out of the photography.
Is the maximum the same at every jump?
Yeah, it's all, that's right, yes.
Okay.
Right. And remember what drives this is the speaker, right? So that's how you can sync the camera with the speaker. So that's how you can do this. Okay, does that make sense? It's a little misleading. I kind of don't like showing this part because you miss all of that stuff. But if you didn't do this, you have to wait a long time to see all this thing drifting like this. So this is a lot of cycles being shown here. You understand what this is? The strobe effect here. You get the same. You can do the same sort of thing, in a dark room with a strobe light. Somebody's moving, and the strobe is. If you're doing like jumping jacks, if the strobe were in sync with your motion, you would just see them with their hands out like this. You wouldn't see the rest of the side. That's what's going on. Okay, it keeps getting even more interesting. So that's a walker. Here's a pair. These orbits are quantized. They'll only occur in certain quanta of angular momentum. Very strange. Here's the schematic of the device. The shaker is like a speaker, and there's the dish, and then you have silicone oil. Okay, now they've done something a little different here. They've actually, you can change the depth of the silicone oil by having the bottom surface of the dish not be flat. And so in other words, there's a region here over to the left, to the right, where the oil is thinner, not as deep, and then have a deeper region in the middle. The droplet doesn't want to go up doesn't want to go into the region where the liquid is thin. If it's in the center region, it'll get bounced off. It'll reflect off the step, like a barrier. And it'll stay confined into that region. Okay, so they're going to watch the, well, there's, okay, 70 hertz here. Amplitude is 0.2 millimeters. That's how much the speaker is shaking. Okay, so you can see it's confined into that region, the deep part of the pool. Can't get into the shallow part. So they're going to watch it. This takes a lot of time, right? To watch this drop, do all this stuff. Okay, we're making a histogram, like a probability plot. So they're making a histogram, which means what fraction of the time of this whole time was the particle seen to be in some little area. And that's what it looks like. Okay, this is resembling if we did the Schrodinger equation in 2 dimensions. We did instead of a box, we had a circular region. We confined it to a circle. There are a lot of solutions. This would be a higher mode, but it's a solution of one of the pure modes, particle in a circle. We'll do something like that later. But you can understand the idea. Here's a careful analysis of that. Okay. All right, and the one on the left is resembles the one on the right. The one on the right is the walking drop you just saw. The one on the left was made by a grad student at Stanford. He put using a scanning tunneling microscope and controlled the position. So he laid a bunch of atoms. You can see these peaks around the circle. That corresponds to putting a bunch, I think they were copper on silicon, if I remember correctly. He just placed them in the circle. And he came back with a scanning tip. Will give you a profile of the electron density created inside of the circle. And that's what I'm saying. The Schrodinger equation solution looks a lot like the walking droplets. So this is a lot like a Schrodinger equation for a particle in a circle. Probability.
Why is there 2 random peaks on the corners?
It's not perfect. These things dropped off in the wrong place. You probably had to do this for a while to get them all lined up nice and neat. That's probably enough to show you. Oh, you can do a diffraction experiment. So you can have the shallow region forming a barrier with a hole in it. So there's a deep pass through the barrier. And then you can shoot these droplets and watch them pass through and collect a scattering experiment with the droplets. And then you can look at the distribution of the droplets on the far side. It's like a diffraction. It turns out to have a diffraction pattern. It has amplitudes a lot like a diffraction pattern. You can do double slits. Amazing all the stuff you can do. The analog is really striking. And it's actually almost quantitative in some ways. Some of the resemblances are very striking. Semi-quantitative comparison from the Schrodinger equation to this, you wouldn't expect it to be even that good. When you understand what's going on here, it's not surprising that there's these wave-like patterns in the probability, right? Because of the particles dropping on creating a rippling in the surface. It's interacting with wave. Okay. So that we're going to hopefully get the experiment. You got to see it for yourself to watch this stuff. You can see though some of it to do this kind of analysis requires special processing of the images, data, and stuff like that. So you're not going to see, like you won't see anything like this. You're just going to see the droplet walking on the surface. So you got it to walk, right?
Yes, sir.
Did you do anything else with it?
Well, the goal was to build a droplet generator so we can do the double split,
Oh,
the
okay.
single split, and build some type of thing that allows us to do the particle in the box, two particles in the box.
Okay. Wow, that'd be great.
Next summer.
Next summer, okay. That was a summer project.
Yeah.
So all of this is on YouTube. You can look it up on YouTube. There's quite a lot of video there of all the experiments that they did. Nicely published and cataloged. Pretty neat work. Okay, so let's see. So what I'm going to show you today, we talked about is the way we were calculating ensemble averages of measurements of the momentum, right? So we originally had the Born rule. We have a wave function as a function of x. So I'm going to use capital psi to be the wave function of x and capital phi to be the wave function of k. So we had this, we formed the probability by squaring this, and then we can form like averages of, for example, x. By integrating like this. Then we discovered that you could do a Fourier transform of this function. You get a function of k and t, so you're transforming over x, which means that you're analyzing the spatial frequencies present in the wave function. So what wavelengths are necessary superimposed together to give you this shape? That's what the Fourier transform. Let's start writing the x over here. Okay. And then we said, so this is the probability in x. We said there was a corresponding probability in k. Well, Q, I'm not sure he does that in the book, but anyway, we understand. There's a corresponding probability for the wave numbers, which you get from doing the Fourier transform. And then we could do things like, what is the average k over the ensemble? Okay, and again, remind everybody here, we're starting off with a state vector, a wave function, which describes how the ensemble is prepared. And then we get to this through the use of the Fourier transform. I'll put this, I hope this doesn't confuse you, right? Are you used to saying the dummy integration variable first? Okay, it means the same thing. Remember, this is just an ordinary product. This is the bin width size of the bin. So you can rearrange the product in any order, right? It's multiplication, it's commutative. So I could write this dx on x.
Is there a reason to do it that way?
Yeah, you're gonna see it. I'm gonna, the order of the symbols are gonna about to matter here. So I'm just trying to clean things up so it'll be tidier when I get there. Okay, but this is kind of cumbersome to work with. It's mathematically well defined. If the Fourier transform is well defined, then I can do this. And we found out there was a relationship between the uncertainty in x and the uncertainty in k, and that corresponded to the Canard uncertainty principle, which we can put into practice by taking an ensemble and dividing it into half. And then one half we perform measurements of x, and then the other half we perform measurements of k or p. Remember, the momentum is h bar k. And then we found that there was a relationship between these two things. There was a lower limit, which has to do with this. If I make a wave function which is confined to a narrow region, I have to have a big spread in wave number to make a superposition that will be confined. Likewise, if I have a narrow spread in wave number, I have a very spread out wave function. Superposition doesn't confine it well. And so that was the Canard uncertainty. Okay, so now I'm going to show you an easier way to go about doing this. Instead of taking the Fourier transform, there's a more direct route. We can form ensemble averages of k directly from the wave function. And this is going to introduce something, you've already seen a little bit of this without recognizing it, without being brought out. We're going to be developing operator formalism for quantum mechanics. So in other words, I want an operator that's going to act on this wave function that will give me, in some way, ensemble averages of the momentum. Okay, and there's a hint about this already. Remember, you had a plane wave in a special case like this. You did a homework problem where you wanted an operator that would pull down the k. Plane. So what can I do to this that would pull down a factor k out front? Derivative.
Take the L.
With respect to x. Right? If I take the derivative with respect to x, what do I get? I k times the wave function. So we've already got a hint about how to do this. To get k, we need a derivative with respect to x. Okay, in fact, to get just k by itself, we need a negative I out front here. So there's already an operator. A little hat. The hat means operator. Usually what we have are differential operators. So k hat had a number. K was a number. The wave number was the number. Now we have an operator, which is a derivative. So we can extract information from the wave function about the momentum. I'll show you how this works. You've already seen a hint of this. Remember also that the kinetic energy had a corresponding part in the Schrodinger equation. Yes,
Is there a hat on top of that K?
not this case.
Okay, but the one that's circled.
This one, yes, that's a hat. So there was, in classical mechanics, the kinetic energy, which written in terms of the momentum is p squared over 2. And we found a term in the Schrodinger equation which was supposed to correspond to the kinetic energy, which was the second derivative with respect to x. In fact, if we square this, k squared minus the second derivative with respect to x. And then if we multiply by h bar squared over 2m, which gets that term in the Schrodinger equation. The it on the wave function in some way corresponding to like an energy. Right? To give us the right dispersion. Okay, so you've already had a hint of this. You've been using it, just didn't recognize it as its form. So I'm about to show you how you can actually use this and look out for this operator. And then we'll see that we can calculate this, the expectation value of k, directly from the wave function without having to go through the Fourier transform first. Very simple when we're there. Got a few steps. It looks kind of complicated on the way. The end result is very simple. Okay, so what we're going to do is this. We're going to start off with this expression. We're going to substitute here. Well, first we notice we get a k, factor k here, then we get phi star phi. And then we're going to find that we can replace that k with a derivative. That we can, in fact, substitute this into here and get an expression involving psi directly, without having to go through the Fourier transform. And this will involve simply something like this. Take the derivative of this complex exponential, gives you a factor of k. That's as complicated as it is. It looks a little bit messy along the way, but that's the essence of it. Next, can I erase? Are you okay? It's a great labor saving in that sense, but there's even more to it than that. There's an interesting aspect to this. Okay, so we're going to start with this. Okay, so by the way, there's an exam a week from today in this class. So we'll start, there's a review and a practice exam on campus. It should be there. I think it is. And so we'll start, I'm far enough along in the lecture, I think we can start reviewing Friday and Monday. And practice exam will really prepare you well for the exam. There's a lot of stuff in chapter 2. It's been a long chapter. Okay, so let's start with this. We want to do this, but we don't want to have this to do first. So here's something that we know. We're going to rewrite this. Rewrite this things in a little different order. Again, it's just all multiplication at this point. I can rearrange them if I want. And I'm looking out for this term here. Got an extra factor of k, which should correspond to a derivative in x somehow. Okay, and we also have this, that phi is the Fourier transform of psi. So what if we tried to Fourier transform this? Take the Fourier transform of this, see what it gets. Is it somehow related to phi? Okay, so we're going from psi, Fourier transform of psi gives phi. What is the Fourier transform of the derivative of psi? So let's transform this. Differs by having taken the derivative of psi with respect to x first. This is going to be related to the transform of psi in a very simple way. Okay, anybody see something that we could do here?
Use the IKX right on the table.
Yeah, right, but we don't have. Well, remember, this is the Fourier transform of this. We don't have this on the table, right? We don't have a generic function. This is an unknown function here. This is part of the transform. We're not taking the transform of e to the IKX. We're taking the transform of this.
Use partial, you integration by parts.
Integration by parts. Let's try that. EX over here. integration by parts. Okay, and we're going to notice this is an integral of a derivative. That's the idea behind the integration by parts, is you get a complete integral in one part here. So this is the integral of the derivative, which means it's the difference in this piece evaluated at the 2 endpoints. This integral gives that. Okay, now if it happens that psi vanishes at the ends, and this term goes away. So let's assume that that's true. Okay, and we're not going to come back and fix this. It's locked in the case. But that has to do with the fact that this integral is defined. It's not going to be defined for a function. Careful, if the function is not vanishing at the endpoint, then this integral might not be defined. So it's not much worse than assuming that the integral is defined. But let's just do that for now. Okay, let's just assume that psi at the end, then we can throw this away. Bingo, here it is, right there. We have a negative sign here. When we take the derivative of the exponential, what do we get? Negative ik, combined with this negative, so we get a factor of ik out front. What's that thing in the integral? Review what we did. We know the Fourier transform of psi, and if we have the Fourier transform of psi, we just found out that we can very easily know the transform of the derivative of psi. We just multiply by ik. Oh, okay. And we have that right here. We have k times the Fourier transform. Okay, so now we can, you have to be careful about this. We're going to take this, put it into here, and then take a complex conjugate, put it in here, do a little bit more work. But it shouldn't surprise you what we get. The following. This is the reason I've been writing these things in that funny order. I can get the expectation value of the ensemble measurement of momentum directly from the wave function without having to do the Fourier transform first. And that's because this k here is like having taken a derivative of psi here. And, okay, this was the k operator. Used on the plane wave. Again, Fourier transforms come from plane wave. Use the k operator on the plane wave to get down the k. All right, so we have a way of getting much easier results than going through all this work. The k operator, derivative in x. So we could have a p operator, which is h bar times k. H bar k operator. So p hat squared is going to be minus h bar squared second derivative with respect to x. Then it comes into the Schrodinger equation in terms of the operator p hat. Sorry, I'm erasing. Everybody okay? We go too fast. Follow. Okay, so let's go back to the Schrodinger equation. This time dependent Schrodinger equation. We can now write it like this. The operator, just take a function of x, multiply the wave function by it. Don't do anything else, so you just multiply it by a function. A operator is the second derivative with respect to x, squared, k squared. And all of this is written sometimes very succinctly as H. H is called a Hamiltonian. Named after Hamilton. Did a lot of very interesting mathematical work in the late 1800s on, it was 1800s, might have been sooner, on dynamics. Operator relating to this. If the potential energy is independent of time, the Hamiltonian is the energy. So if E of x is independent of time, H is equal to E. So what we have is an energy operator. If the potential is independent of time. This is like an energy operator. Okay, so now this is actually leading us to something very interesting. It's going to be some of this showing up, well, a lot of this showing up in chapter 3. What we're finding now is the structure of the mathematics. Before, to do particle dynamics, we had Newton's law. We have F net is equal to dp dt. You have to put in the net force, we have to put in the forces acting on the particle. The net force would then change the impetus, change the momentum. That led to a second order differential equation we would have to solve. And so now we have differential equations, ordinary differential equations. The mathematical structure now is different for quantum mechanics. We have a probability amplitude, which gives us information about ensemble measurements. We have an equation that gives us the evolution of that probability amplitude. And we know how to go from the probability amplitude to a probability and ensemble averages measurements. Extracting information from the wave function in the business of these operators like k hat or p hat. So the mathematical structure of quantum mechanics has a combination of this complex wave function and operators acting on the complex wave function. Okay. So one more thing. I've got a couple of minutes here. So it'll help you to understand better the significance of this K operator. Let's suppose I have some function evaluated in the vicinity of x. So epsilon is a small displacement from x. And I want to see how this function depends on epsilon, having defined the reference points. In the vicinity of x, how does this function vary with epsilon? Okay, so here's some function. And we're picking a particular x. And taking a step, epsilon, in some, a little bit to the right. We want to estimate the value of the function here, knowing things about the function at x. All right, well, the first approximation would say that the function at f plus epsilon, well, that's pretty close to the function at x. Pretty close. So the crudest thing to do would be to say f of x plus epsilon, well, that's approximately equal to f of x. Now you can say, well, that would be pretty good if it doesn't have a steep slope to it. But if it's got a really steep slope, that's not going to be a very good approximation. So the next thing would be to say, suppose we use the slope. So we know the value of the function and we also know the slope of the tangent. Well, if we know the slope of the tangent, why don't we extrapolate? And take another guess, which is going to be closer, involving the slope. So we're going to involve the slope. And we're going to say, well, it's f of x this much plus this much. Right, this is the run. We're looking for the rise. What's the rise in terms of this, the run and the slope?
F of x prime times dx.
All right, that improves our estimate of f a little bit to the right, to take into account the slope. And you can keep getting better about this. Well, okay, there's the slope, but there's also the curvature. So if I take into account the curvature, then I would get another term, and it would turn out to involve epsilon squared. I won't do that for you. You can keep on improving on the approximation. Okay. I'm not going to go on into the depth of this, but there's a lot of interesting stuff in this, what I'm talking about here at the beginning. But I'm just going to focus on this. So to a pretty good approximation, if epsilon is not very big and if the curvature is not very big, this is really a good approximation. It's an approximation. But notice, how did we get the value of the function over here? We use the function and the derivative. Write this operator 1 plus epsilon d by dx. Acting on f of x. This operator translates the function. Right? We're evaluating the function sliding over a little bit, somewhere to the right. So the derivative operator accomplishes the translation. This, and there's a factor of I haven't explained here. There's a reason for introducing the I. It's not really important in this. So just focus on the derivative piece. This accomplishes the translation, the wave function. It's a translation operator. Related to the translation operator is the generator of translations. That's the official, that's the common terminology. Generator of translation. The derivative is the generator of translation. Okay, put your thinking caps on. So multiplying by h bar to get p. What is momentum? Measure of the impetus. What is the impetus? Cause of locomotion. The operator, which is the generator of translations in x, corresponds to the measure of the momentum, which is rather corresponds to the operator. It has to do with momentum, which is the measure of the impetus, which is the cause of translation, cause of locomotion. It's not an accident. So this understanding of the content of the operators, a very important aspect of quantum mechanics. In other words, quantum mechanics comes down to two things: the wave function and the operators. And understanding the relationship between those, how to use the operators to act on the wave function, extract ensemble average predictions about measurements on an ensemble. Cool. Okay, so I'm done for today. Have a question? Yeah, Mr. Green.
Operators on the right. In a sense, more exact than the one that you.
Yes, right.
There's still statistical, related statistics, but that is.
So the proper translation is no, yeah. Writing it like that. I epsilon times k hat, the operator, translation operator. And there's a reason for writing this. This is a funny thing here. It's an exponential of an operator, right? We're not used to dealing with that. But that's why it's this. If you continue the series, Taylor series, continue the Taylor series, this generates the Taylor series. This is the generator of that Taylor series. The derivative operator is the generator of Taylor series. And this is the formal. It's written this way for various reasons. There's another factor of I here that cancels that negative I there, right? If I wrote it without the, I would write it like this. Okay, this generates the Taylor series in epsilon. This, so I'm doing an exponential of this operator, so I define it like I did before. 1 plus this operator, call it A over n, raised to the n, if the limit is n goes to infinity. This is e to the a half, a is half. So that's maybe more than you needed to see, but some in the class are able to connect this now to other things that they've learned. The most important aspect isn't the connection with the Taylor series, it's this. That the impetus to cause or impetus is the cause of locomotion. And in the mathematical structure of quantum mechanics, the translation operator, the generator translation related to the momentum. Okay, any other questions?
You get to see this hat operations. You only see this in like quantum, like the hat operator.
Yeah, pretty much. That notation is pretty special with quantum. Hat has other uses like in vectors, unit vectors. Yeah, so you have to know from the context what the hat means, what it's bold. So in a book on quantum mechanics, if you see a hat, it's probably an operator. Not always, but probably.
You ever mix them together before? You ever have, is that ever saying you with them?
In my class, no. No. So we had hats for mechanics and them corresponding to the unit vectors. The hat here has a different meaning.
Such a good message.
So we're not going to be doing three-dimensional things very much, only just a little bit at the end. So that would be where you might see some confusion there. You got three-dimensional things. You got hats for unit vectors and hats for operators. That can be confusing, right? So that's where there might be some potential confusion, but there isn't in this book. There's no hat that corresponds to unit vectors, I think. That would be a potential problem. Any questions? Other questions?
Yeah, it would be a potential problem because you got the hat operator.
Yes. All righty, so we'll see you on Friday.